Gary, I'm never saying that quantum mechanical cause and effect is unicorns. I'm simply saying that it's not determined. And you say that, you do say, you just don't understand, I guess, the point of me saying that your idea of cause and effect is one to one, one cause, one effect. Yes, one at a time. Okay? And if you don't believe that, well, quantum mechanics says that because there's discrete events that are underlying all of these macroscopic causes and events. And it's always the one-to-one energy transfer of a photon emitted somewhere and absorbed somewhere else, pretty much, or some other energy-carrying subatomic particle. And you associate all this stuff with randomness, but the people that study quantum mechanics don't, because though there's a lot of randomness in one event, when you do a billion events, the probabilities come out, and you can reliably know if you roll a dice a bunch of times that you will get a particular pattern out of them. And if you do it one time, you're just going to get one number. But if you do it thousands of times, you'll start to get a spread of numbers. And you keep saying when they ever invented. I've told you what they've invented with quantum mechanics. There's quantum cryptography, okay, and there's the tunneling microscope. These aren't randomness. The tunneling microscope can take pictures of metallic surfaces that show the atoms involved. That's pretty good. To show the atoms. It's not a random picture. No, it's a very regular picture that works on statistics and probability, and uses statistics and probability to get truth out of a bunch of events that individually have unpredictability. You get the predictability through the statistics, through a large number. And we did discuss what it might be used for in biology, because there was a research paper recently, you just threw it out of your mind, fine, but there was a research paper recently that was claiming that photosynthesis uses quantum effects in order to get its very high efficiency percentage in collecting solar energy. That's the kind of thing. What don't you understand about efficient energy transfer being useful? That would be useful to our biological evolution, and it's part of physics. Like we were talking about physics, what the physics dictates, it's there. It's useful to us, but you're saying there's no way we would use it. We keep our hands off of that technology while we're evolving. Yeah, I don't think so. I don't think so. And I never said there was any unicorns or anything of that kind of spontaneity, ever. That's your idea, because that's what you think it must mean when I break your little one-to-one thing of cause and effect. Okay, the model you need of cause and effect is on the quantum level. A photon is a cause. It hits an atom. The atom becomes energized. That's the effect. The atom will then emit photons eventually. That also is an effect. It can emit a photon that's like the original one, or it can emit a bunch of smaller photons. It can even have another cause before it emits another photon, getting another energetic state, and then it can emit a higher energy photon, or it can a group of lower energy photons again of a different sum total. That is, many effects adding together to one, many causes adding together to one, or one becoming many. And that's the way it looks, and you want to say, oh, but it's all causal. Yeah, it's causal. That's the whole reason that geniuses like Richard Feynman believed in the many histories approach. They're like, yeah, it's not random. All three things happen. And the question is why we take one route rather than all three. That's the question. And as far as, the scientific evidence has showed that God doesn't play dice with the universe, no, you're wrong. Einstein said that because all the evidence was showing that God plays dice with the universe. But I don't think that's such a big deal, because when you roll a die, it comes up like a die. It doesn't turn into a fish. The fact that it's really randomly split between 1 through 6, and maybe not in a die, but at the atomic level, that it's really randomly split to these various proportions based on the probability waveform, that's not a big deal, because you roll a die, it comes up one of the 6 sides. It doesn't come up a fish. So, you have some predictability. You can use that thing. You can use it for a game or a decision-making process. You can use that thing, and you can know that it's going to be fair. If you decide every day, 1 through 6, you roll a die, and that person gets a piece of pie. The same person might get a piece of pie 2 days in a row, but after you do it after thousands and thousands of days, everybody will be pretty much even on how much pie they've gotten. Okay? And you can't be sure, because you could roll the 6 a million times in a row. But how likely is that? Not very, and there's your probability. There is your probability, and you rely on the probability, and that's how you make predictable things, by accepting things the way they are. Now, your idea of cause and effect is this ancient, totally discredited idea of cause and effect. And you need to think of cause and effect more in terms of energy transfer and conservation of energy. All of you do that believe in anything remotely like this determinism. You need to understand cause and effect in terms of what it really looks like on the fundamental level, which is energy transfer. Okay? Energy transfer. And it looks on a macroscopic level like what we call cause and effect, but when we're thinking about these details, oh, well, we found the differences in the physical sciences. I don't know why you want to follow the physical sciences right up to, 1890 and then get off the boat, but the rest of us that stayed on the boat, we've sailed a little distance now, and we actually do know the practicalities of these quantum phenomena. We can't explain them all, but we do know things like that cause is really energy transfer, and everything's energy. We know that. Okay, so.